Welcome to the deep dive. We are kicking off today with something, well, kind of fascinating in AI research. It's called Moravec's paradox.
Ah, yes, the idea that the hard stuff for us humans, like logic or chess, is
Hmm.
relatively easy for AI.
Exactly. But
Yeah.
the things a baby does without thinking, like catching a drop toy or knowing a ball still exists when it rolls behind the sofa, that's incredibly hard for even advanced AI.
Right, that's the gap in what we call physical common sense or intuitive physics. And that's what we're really digging into today. There's this paper, Intuitive Physics Understanding Emerges from Self-Supervised Pre-Training on Natural Videos.
Okay.
And it introduces a model called V-JEPA, that's Video Joint Embedding Predictive Architecture. It's a pretty significant in how it approaches getting machines to understand the physical world.
So our mission today is to really get under the hood of this. We want to unpack how V-JPEA learns this physical intuition, right? And how its whole setup, its architecture, is fundamentally different from, say, a big language model or those models that just predict pixels.
And importantly, the thinking behind it. What's the conceptual leap that lets it have these aha moments about physics?
Yeah. So if you're listening and you want a proper technical and conceptual understanding of how AI is moving beyond just language into building these internal models of the physical world, well, you're definitely in the right place.
Let's start with that core human ability then, intuitive physics. It's
Yeah.
absolutely fundamental.
It really is. It's how we navigate everything. Expecting objects to,
Okay.
stay solid, not just vanish.
Object permanence, stability, continuity, all that. We see it
Mhm.
super early in infants and even in animals too. It's basic cognition.
So how did AI try to tackle this before V-JPEA came along?
Well, historically, there were sort of two main camps.
Hmm.
First, you had what are called structured models. Think of these as trying to build a little physics engine inside the AI.
Like hand-coding the rules.
Pretty much. It was based on this core knowledge idea from cognitive science that maybe there are innate systems for understanding things like objects in space.
Mm.
So researchers tried to build in these abstract representations directly, like a mental game engine, as you said.
But if they were told the rules, why didn't that just work? Seems logical.
They ended up being too rigid, too brittle, because everything was pre-programmed. They just couldn't handle the messiness and the sheer variety of real-world videos. They couldn't generalize.
Okay, so that's one approach. What was the other?
The complete opposite, really. Pixel-based generative models. These models said, forget hard-coding rules, let's just learn to predict what we'll see next, pixel by pixel.
Trying to reconstruct the future frame.
Exactly. But the problem there was, well, it's incredibly inefficient. Imagine trying to predict every single blade of grass moving in the wind or every ripple on water.
Yeah, you'd get bogged down in totally irrelevant details.
Right. The model wastes huge amounts of computational power, predicting noise, predicting textures changing slightly, instead of focusing on the important stuff like, is that car going to stop at the red light?
Okay, so structured models were too rigid, pixel models were too noisy, and this is where V-JEPA finds its niche.
Precisely. V-JEPA proposes this middle ground. The core idea is prediction shouldn't happen at the pixel level. It should happen in an abstract representation space that the model learns itself.
So in its own internal high-level understanding of the world, not the raw visual data.
Exactly. It's learning its own concepts, its own features. Instead of being told, this is an object, it learns object-like representations because those are useful for predicting what happens next at a high level. It's trained to essentially ignore unnecessary low-level stuff.
Hmm.
This actually lines up quite nicely with ideas from neuroscience, like the predictive coding hypothesis, the theory that our brains are constantly making high-level predictions about the world and updating based on errors. V-JPEA kind of operationalizes that for video.
Okay, this abstract prediction space idea is crucial. Let's get into the architecture. You said it's based on a vision transformer, a VIT. How do you pieces fit together to actually predict in this latent space?
Right, so there are three main parts working together. Think of it as a predictor trying to anticipate what a stable teacher network will see.
Okay.
First, you have the context encoder, let's call it Phi-NO. This network gets fed a damaged version of the video clip. Large chunks, both in space and time, are masked out, hidden from it.
So it only sees fragments.
Exactly. And its job is to look at those fragments and produce a high-level abstract summary, a representation vector of what it can see.
Okay, encoder number one sees a broken video. What's next?
Next is the target encoder, let's call it Phi-NAGU. This one is the stable reference. It gets to see the full, uncorrupted video clip for the parts the first encoder is trying to predict. Its job is to produce the correct target representation for those future or masked out parts.
And crucially, its weights are related to the first encoder.
Yes, and this is really important. Its weights are an exponential moving average, an EMA, of the context encoder's weights. So, theta follows the theta, but smoothly, slowly.
Why that slow averaging? Why not just copy the weights directly?
Because the context encoder is constantly learning and changing rapidly as it sees new data. If the target encoder just copied its weights instantly, the prediction target would be jumping all over the place. It would be trying to hit a constantly moving target.
Ah, I see.
The EMA stabilizes things. It provides a much more consistent, reliable target representation for the third component to aim for. It stops the model from collapsing or getting stuck in trivial solutions.
Okay, so context encoder sees fragments, target encoder provides a stable, smoothed target representation of the whole thing. What's the third part?
The predictor, theta,
Yeah.
this is a smaller network, often another transformer block. It takes the abstract representation from the context encoder, the one that only saw the fragments, and its sole job is to predict the abstract representation that the target encoder generated, the one that saw the whole picture.
So it's predicting representation from representation, not pixels from pixels.
Precisely. And the training goal, the loss function, is simply to minimize the difference between the predictor's output and the target encoder's output, usually using something like an L$1 distance.
Right, minimizing Albert PFV, so mathematically forcing the model to minimize that error between the predicted representation and the target representation. What does that actually do to the kinds of features the encoders learn?
It forces them to become semantic. Think about it. If you mask out, say, 80% of the video, the only way the context encoder can provide enough information for the predictor to guess the target encoder's view of the future is if its representation captures the really important high-level stuff.
Like the object's trajectory or its identity.
Exactly. Yeah. And that's to understand that a ball rolling behind a box is still there. It will come out the other side, even if it can't see the pixels for that part of the video. It has to learn abstract concepts like object permanence and continuity,
Yeah.
because those are the only things stable enough to allow prediction when most of the input is missing. Low-level details are useless for that kind of long-range prediction with heavy masking.
Okay, that makes sense. So how does this fundamentally differ from, say, what a large language model is doing when it predicts the next word?
The core difference is the nature of the prediction space. LLMs predict just things, tokens, words in a sequence. It's usually causal. Predict the next token based on the previous ones.
Right.
Pixel prediction models like Video MAE-V2, which is another VIT-based model, are predicting in the pixel space. They're trying to fill in missing pixel values. Still very low level.
Still focused on the appearance.
Yes. V-JPEA is predicting vectors in a continuous high-dimensional latent space. And the pre-training task isn't strictly causal prediction. It's usually block masking, taking out big 3D chunks, height, width, and time. This forces the model to reason about relationships across larger spatiotemporal gaps, encouraging it to learn object dynamics rather than just smooth motion or texture completion. That continuous abstract prediction target seems to be the real key.
Interesting. And just quickly on the technical side, how does it handle the video structure, the time dimension?
It uses standard tools adapted for video. The Atom W optimizer is common. And for position information, since it's a transformer, it needs positional embeddings. They use ROPE, rotary position embedding, but adapted for 3D data height, width, and time, so the model knows where and when patches occur in the video clip.
Okay, so the model learns these abstract representations by predicting them. But how do we actually know it understands physics? It hasn't been given physics lessons.
Right, we need a way to test its intuition. And for this, the paper cleverly borrows a method from developmental psychology used to study babies. It's called the violation of expectation, or VOE, paradigm.
How does that work with babies or AI?
With babies, you show them two scenarios. One is physically normal, a ball rolls down a ramp. The other violates physics. Maybe the ball stops midair or passes through a solid object. Babies tend to look longer at the impossible event, indicating surprise, a violation of their expectations.
Okay, so they measure looking time. How do you measure surprise in V-JEPA?
It's actually quite direct. After V-JEPA is pre-trained, you feed it the initial frames of a video, the context, tollers. Then you ask it to predict the representations for the upcoming frames.
Yeah.
Then you show it the actual future frames and get their true representations using the target encoder. The surprise metric is simply the prediction error. How far off was the model's prediction from the actual representation of what happened?
So if the video shows something physically impossible,
the model's internal prediction, based on its learned physics model, will be wildly different from the actual representation of the impossible event it's suddenly seeing. The prediction error, the surprise score, shoots way up.
That spike tells you its internal model of how things should work has been broken.
Exactly. It's a quantitative measure of violated expectations.
And the results using this metric were pretty impressive, right? That 98% accuracy figure on the IntPhys benchmark sounds huge.
It is remarkable, especially being zero-shot, meaning the model wasn't fine-tuned on any physics tasks after its initial pre-training on general videos. It could distinguish plausible from implausible videos almost perfectly on that benchmark.
Now, we should add a bit of context there. The IntPhys benchmark, what kind of physics is it testing? Is it super complex, real-world stuff?
That's a fair point. IntPhys mostly uses simplified, simulated 3D environments. Think blocks, balls, ramps. It tests core concepts like object permanence, shape constancy, gravity in a controlled way. It's not messy, real-world video with complex materials or interactions.
But still, hitting 98% on those core concepts, zero shot, is significant. And comparing that to human performance.
On that specific test set, V-JPEA performed comparably to, or in some cases even slightly better than, the average human baseline collected for that benchmark.
Okay, so why did V-JPEA nail this when other powerful models didn't do so well?
Well, the comparison is pretty stark. As we said, V-JPEA is way above chance. Those pixel prediction models like Vision-JEPA EV2, they hovered around chance level. They just couldn't reliably spot the violations because they were lost in the pixels.
And the big language models, the multimodal ones.
That's maybe the most surprising part.
Yeah.
Huge models like Qwen 2, VL-7B, even Gemini 1.5 Pro, massive models trained on vast datasets, including text and images. They also performed around chance level in these intuitive physics video tasks.
Wow. So throwing more parameters and more general data at the problem didn't help with the specific kind of physical reasoning.
It really suggests that the inductive bias of the model, the way it's structured to learn, is more important than just scale for this particular capability. Predicting in the abstract latent space seems to be the crucial architectural choice.
For breaking it down, what specific physics concepts does V-JEPA seem to grasp well?
It really excels at things related to inherent object properties and scene layout. Object permanence, knowing things, still exists when hidden. Continuity objects move on connected paths. Shape constancy objects generally keep their shape. And basic support and gravity things fall down, need support. It gets the what and where of objects pretty well.
But you mentioned limitations earlier. Where does it struggle?
Yes, the paper notes it didn't show strong performance on categories that require really precise modeling of how objects interact. Specifically, solidity objects not passing through each other and collision dynamics.
Why might that be?
Couple of hypotheses. One, maybe those kinds of direct, clear collision events are just less frequent in the massive, diverse training data sets like how to 100M compared to, say, just objects existing or moving. Two, maybe truly understanding collisions requires a different kind of representation, perhaps one linked to potential actions or forces, which V-JEPA, as a purely passive observer, doesn't have.
Right, it doesn't act in the world, it just watches. That leads nicely into the ablation studies, figuring out which design choices really mattered. This is where it gets super interesting, right? What did they find was essential?
Yeah, the ablations were fascinating. They systematically changed parts of the model or training setup to see what broke the physics understanding. Three key things stood out, and it kind of challenged some standard AI scaling narratives.
Okay, what's the first one?
Training data. And not just how much data, but what kind. They found that tutorial videos, specifically the How to 100M dataset, where people are demonstrating tasks, manipulating objects, that data led to the best intuitive physics performance.
Better than just videos of general actions or motion.
Significantly better than datasets like Kinetic 710, action recognition, or something V2, basic human object interactions. It suggests that learning from video, where the structure and interaction are often clearer, perhaps more goal-directed, is really beneficial. And interestingly, even using just a small fraction, only 128 hours of unique How to 100M video, still resulted in over 70% accuracy on IntPhys.
Wow, so quality and type over sheer quantity, maybe.
It seems that way for this task. The nature of the interactions in the data seems key. Second finding, model size.
Does bigger always mean better here?
Bigger does help, yes. A larger vision transformer backbone, like VITH, performed better than VITL. But, and this is important, even a relatively small model run 115 million parameters still achieved over 85% accuracy. It showed what the paper called robust understanding.
So you don't necessarily need a trillion parameter model for this core physics sense.
Apparently not. Good architecture and the right kind of data seem to get you most of the way there. Scaling helps refine it, but isn't the fundamental source of the ability.
Okay, data type matters. Size helps, but isn't everything. What was the third key finding?
The pre-training task, specifically the masking strategy. This was maybe the most surprising. While different masking strategies, like the block masking V-JPEA uses versus simpler random masking or causal masking, do affect performance on other downstream tasks, like action recognition,
Mm-hmm.
they had much less impact on the intuitive physics benchmark scores. Performance stayed high across different masking approaches.
So the exact way you hide parts of the video isn't the critical factor for learning physics.
It seems less critical than the core idea of predicting in the abstract representation space.
Yeah.
As long as you're doing that, the model seems to pick up on the physical regularities robustly, regardless of the specific masking details. That prediction objective itself seems to be the powerful driver.
Okay, so let's try and wrap this up. What's the big takeaway here? It feels like this challenges some long-held ideas.
I think it does. The main implication is that something as fundamental as intuitive physics, which some theories propose might need to be innate or explicitly built-in core knowledge, might actually just emerge.
Emerge from a general learning principle.
Yeah, emerge from simply trying to build an efficient, abstract, predictive model of the world from sensory data. You don't necessarily need to hardwire object permanence.
Yeah.
The model learns it because it's an incredibly useful and stable abstraction for predicting future states in its latent space. It shifts the focus from innate modules to the power of self-supervised predictive learning at the right level of abstraction.
But it's not perfect yet. What are the big limitations we should keep in mind? Where does this need to go next?
Definitely limitations. The paper mentions a few key ones. First, memory. These models currently operate on very short timescales, like 3 to 4 seconds of video.
Right, you mentioned the goldfish memory analogy.
Exactly. That severely limits understanding complex long-duration events. Second, uncertainty. The current V-JPEA makes predictions, but it doesn't really quantify how confident it is. Biological systems are constantly dealing with uncertainty, making probabilistic judgments. That's missing here.
And the interaction problem.
Yes. The third point is the lack of an action channel. V-JPEA is a passive observer. To really get things like collision, solidity, maybe even causality, the model might need to be embodied, or at least have a way to model the consequences of potential actions. Learning by doing, not just watching.
Okay, so still lots of room to grow. That leaves us with a really interesting thought to end on, something for you, the listener, to think about. If a model can learn fundamental physical concepts like object permanence, not from explicit instruction, but just by finding efficient ways to predict the future in an abstract internal model, does that suggest that maybe, just maybe, the path to more general AI isn't solely about massive computation and data, but about finding the right kind of abstraction, the right level for modeling and predicting reality efficiently?
A very provocative question indeed. Is intelligence less about brute force and more about finding the elegant predictive representation? Something to definitely mull over.